Cool, thank you, Peter. I'm going to share my screen. Okay. Yeah. Today we're going to discuss about a paper called Temporal Cycle Consistency Learning. So first thing first, what ML problem does this paper solve? Yeah, this paper looks into how we can understand, learn the representation of temporal correspondences, temporal reasoning in videos. So if you can imagine in videos, there are like action phases, like if someone plays basketball, baseball, first, like we can see the stage and how this frames change temporally. And this paper wants to learn the embeddings, the representation of these temporal correspondences. And then what's the application and why is it important to know this representation of these temporal correspondences? The application's quite varied. I think we can look into this page. They have these webs that I think it makes clear what are the applications of this. Like one application is that we can have this synchronous playback. So let's say we have different videos with different pace, for example, and we can have this videos alignment in terms of time, so that like they happen in the same pace. Another interesting application is like, let me just play this. So if, for example, we have this boring sound, and then we have another video that doesn't have the sound of this boring action, then we can translate or use the boring sound from the first video to the second video so that they are aligned in time. So we can transfer this sound. Another application is like we can also get a more fine-grained information from videos. If like, let's say we want to play the videos in slow motion, means we want to get a more like granular representation of each action in the videos. Or also we can see the anomaly that happens in the videos. Like if normally the process of someone lifting weights is like this, like certain normal phases, but then if someone falls or something is not right in that sequence, then we can detect that. Okay, so back to the paper. That's some applications that we can do if we can learn these embeddings between these temporal correspondences. And what's actually the main contribution of this paper? The first contribution is that this new self-supervised learning called this temporal cycles consistency, TCC. And also this TCC is good to be combined with other self-supervised learning in videos. Like we can look into it later. Like they, from their experiments, they conclude that if they combine TCC with time contrastive networks or TCN, the performance is better. Okay, then here they really emphasize that this is self-supervised and this work well in few shot classification setting, meaning that we don't need many labeled data. And why? Why in this case, being able to self-supervise and not having multiple not having many labels are important. Okay, you can, yeah. First, we can imagine that it can be very laborious for humans to label each frame in a video. Second point is that labeling frames in video can be ambiguous, right? Because it can like really vary on how granular we can break down the videos, and then like how we can label each of them. So this ambiguity in labeling, and then the fact that it's very laborious, makes it quite important if we can come up with self-supervised learning that can work in few shot setting. Another point that they want to sell here as well is that with this training method, they don't need explicit correspondence between different video sequences. So like imagine if we want to collect data of like a particular action, like someone playing baseball, and then we use multiple cameras coming from like different angle. It will be difficult to like align this, because like different angle and like this, it can, they are not aligned, and the fact that we need to manually align them or make it like very explicit rule on this will be very difficult. And here they want to make this method to not assume these explicit correspondences and learning by itself. Okay, I think that's about the background. Okay, some related work here. One concept that they use here is cycle consistency. I think we can dig into it later when we're talking about this in the next section. So there's a few quite popular implementation of this cycle consistency, like in GANs, or they mentioned here also like Saikada, which I had never heard before. But it's in this case they need this particular domain or these image transformations that might not fit our use case, because again we don't want to have explicit correspondence between these frames in the videos, and we don't have like particular domain as well. Same case with this other methods in video alignment. Yeah, and this action localization and parsing, which I don't think it's something, oops. Okay, and in terms of the loss that we can see later, they use the soft nearest neighbors, and yeah, I think that's the main emphasis here. They use the soft nearest neighbors. Okay, so let's go into what does this cycle consistent representation learning is. So if you look into this figure 2, here we have 2 videos. Each video has their frames, which corresponds to the progression of each action. We run encoding so that like every phase here is encoded to like a certain representation. And okay, let's say the first video has the sequence is called S, and then for the second video, the sequence is called T. The first video has length N, and the second video has length M. So for a particular point, like this particular phase, each dot here represents the phase, the frame in a video. let's say we pick like one particular frame in the first video, and then we want to find which frame in the second video that has the closest distance in the representation with this point. So if we call this point is like, they have feel like UI, U represent the embeddings of for the first video. We want to find which embeddings in the second video, V, that is the closest, and it's called, they refer it as J. And then what they call cycle consistent is that when we want to map it back to the first video, we want it to map back to the same point. So this example, this point is the example that is cycle consistent because the point in the second video that has the closest distance with this particular point will map to the same original point, where this other example, this represents the cycle consistency, the cycle inconsistent, because when we map back the points in the embeddings of the second video, it doesn't map back to the sorry, like this first video. Yeah, this doesn't, they don't map back to the same points. So the goal, the objective of this training is that we want to maximize the number of cycle consistent frames between these two sequences of videos. The requirement of the dataset here is that these two videos needs to belong to the same actions. Like if this is about playing baseball, the other video must also be playing baseball. It cannot be pouring milk, for example. Okay. And how? Okay, let's go into this loss. Anyway, is there any point anyone wants to make? Please say something.
No, I think one thing that I thought was really cool, and you just mentioned about the paper, is that the only requirements that you have are that the two videos that you're comparing are of the same action or of the same event, because that's actually a pretty loose requirement for the data. So it doesn't really have to be labeled that much at all. There's no like fine grain labels in it. So I think that's really cool.
Yeah, I agree with that.
Sorry, I want to say, yeah, I definitely agree with what Peter said, because when the paper was talking about the same action, like pouring into something, the container size could change, and the position of the angle and all of those things. So yeah, I agree with that.
Cool. Okay, let's go into this loss that they use here. There are two different loss functions that they use. First is the cycle back classifications. Second is cycle back regression. Okay, let's dig into the first one first. So actually, it's pretty straightforward in general, I think. Basically, the idea of these soft nearest neighbors is like similar to like softmax. We want to find which point in this. We want to find, they call the soft nearest neighbor of each frame in the first video from the frames in the second video. So we found, so UI, U is the first video, V is the second video, I is the particular point in the first video, J is the particular point in the second video, and we want to find which J has the like which j is the nearest neighbor in, sorry, which j is the nearest neighbor for I. And I think the idea here to use soft nearest neighbor, in my understanding, but please someone corrects me if I'm wrong, is that because the idea of soft is that we don't want to necessarily penalize until they have like zero distance, like mapping to the same exact point, but more like to have a close representations. So it's not making sure like they are like exactly the same, but just like they are for these 2 points, they are the closer points compared to the others. And then after that, from the second video, we want to map back to the first video U by simply just using this cross entropy loss for like classification problem, where the labels are the frames in U, or the first video. So it's just like to find which frame in U is the class that this Vj belongs to, and we call this map back point is K.
Inneke, I think the reason why they use soft nearest neighbor is because it's differentiable. So if you actually if they did if they did a hard nearest neighbor, there would be like a max operation.
Oh yeah.
And then you wouldn't really be able to. Would you be able to differentiate? I don't think so, because it would be like predicting a class. So I think that's the reason for the soft nearest neighbor.
Yeah, thank you, Peter. Okay. And that's the first loss function they use. Then why they need this another loss function that is called cycle back regression? So if we see that first loss function, we actually don't care whether the mapping back in U is far from the correct frame or not. So we penalize it same way if the class predicted is this point, which is very far away, or only like 1 frame away. And now we want to take into account this distance between this predicted class, predicted frame in U with the correct frame. And that's why they introduced the cycle break regression loss. So in this case, after we've compute this soft nearest neighbor V in the second video, we want to have this Gaussian prior to map it back to U, and we put that the mean or the peak of this Gaussian distribution in the right class. So we want to minimize this term, because if you can see here in the image that the ideal case that we want is that we will fall in this peak, which is the mean of the distribution, but the farther we go, we will penalize this distance. So I think that's the main idea of this loss, and then they put this regularization term here, and they also put explanation here that they put the variance as in the log form for the sake of numerical stabilities. So yeah, the whole training process can be seen here, that for each frame we will convert them into embeddings with a pre-trained encoder, and then we will find which is the soft nearest neighbor in the second video relative to the first video. And then because we want to penalize less if the predicted frame is close to the correct frame, then we introduce this cycle break regression that basically will have this peak or mean of discussion distribution in the right frame in U. Okay, is there anything we want to dig further? Any correction? Any comment? No? Anyway, I cannot see anything besides this. So.
Nothing for me.
Okay. Cool. Then let's go more to these implementation details. For the encoding network, they use they use ResNet 50 when they use this ImageNet feature. So when they don't train from scratch, but they also have another experiment when they train from scratch and they use a smaller model, which is this VGGM. I'm not really familiar with this evolution of image encoder, so I don't think that's also the main point of this paper. For the data sets, they use two different data sets. The first is called pouring, which is more about the objects that being interacted with. I imagine is like when we pour the liquid, milk, water, etc. And the second data set is called pen action, like human doing sports. For the labeling, as they mentioned before, they don't need many labels. They only label the key events. So yeah, here events corresponds to the frames in the videos. For the evaluation, there are 3 measurements that they did. The first one is the phase classification accuracy. So this is pretty straightforward, that it's just like SVM classifier to predict like which label, to predict the predicted label for each phase or frame in the video. Second measurement is the phase progression. Here we want to see like how good is the progress of each phase or each action in the video. And what we want to see here is the difference in timestamps between any given frame. So I guess we want to see here like how big is the difference if we want to say like someone just grab the ball until like they finished throwing the ball. And the third one, which I think the most interesting one, is the candle style. In this case, we don't need any labels, unlike this phase classification accuracy, for example. In this case, we have a pair of videos, and then for each pair, we will sample we sample a pair of frames from each video, so we know how the sequence of this pair. Like we know, like someone will need to grab the first. Someone will need to grab the ball first before they can swing for this baseball, because they are like in this sequence of the videos. And then we want to see if this sequence is kept in this by the model. So if the model knows that the sequence that it predicts is correct. So it's self-supervised way, because we just need to take like 2 different points in the sequence in this video, and we will need to see if the model can see that it's correct or not. So yeah, they call it concordant if they are in the right sequence, and discordant if they are not in the right sequence. One drawback of this evaluation way is that if there are repetitive frames in the video, this will not be accurate, because imagine if we because like if 2 actions are actually like action B happens after action A, but then if action A happens again after action B, this sequence will be messed up and will be hard to see which one is correct, because they happen repetitively. That's about the evaluation. For the baselines, they compare with 2 other self-supervised learning in videos. The first one is called Shuffle and Learn. Here basically, we randomly sample triplets of frames, and we will predict if those frames are in order or not. So this training method will see if we will emphasize on the order of those actions in videos. And the second one is time contrastive networks, or TCN. In this case, we sample n frames from the sequence, and those frames become the anchors. So anchors is a term that is used in metric learning or like contrastive learning, that this is the first positive pair. And then we will sample, sorry, it's like anchor is like the first, like our target sample. And then for each anchor, we will sample other positive examples within a fixed time window. So those 2 samples will become positive pair. What I understand from this training method is that because they sample the positives within a fixed time window, they might not have the correct order of sequence, because we can sample before that particular phase or after, as long as they are in this time window. But correct me if I'm wrong. And they also compare when they combine this TCC with Shuffle and Learn, or combine it with TCN. And I think main takeaways from the experiments here is that the performance boost is the best when they combine TCC and TCN. Okay, yeah, we can go in more details of these results. So first thing, they combine the ablation study they compare with the mean squared error of this cycle back regression loss and ignoring the variance. And they showed that using their cycle back regression that take into account the variance is better than ignoring this variance. Second thing, they compare it when they learn in self-supervised manner from scratch. So they use a smaller encoder model, the VGGM. In this particular case, this TCC performs better than the other two baselines. Yeah, especially when there is limited label data, which they already mentioned a few times. Second, so the next experiment setting is that when they don't train from scratch, they use ImageNet datasets with ResNet 50 encoder, and they fine tune on it. And here, they found out that the best performance is achieved when this TCC is combined with VCN, which they suspected because this TCN will help to reduce the overfitting, so it acts as like regularizer when we train with TCC, because in TCC this is what I think, but I'm not really sure, because this TCN doesn't for decision is okay to have these frames not in order because the sample is positive within a fixed time window, so they are not necessarily in the same order. Is this the part that become the regularizer of this TCC, or is there any different characteristic of this TCN that helps with this TCC?
So my thinking for the increase in performance is because the evaluation task is neither of the two training objectives, and possibly you overfit to the training objective when you're just training using TCC. And so combining the two kind of regularizes the network so that it doesn't overfit to that training objective. So there must be structure in both of those training objectives that's related to the evaluation problems that they're using. And so it kind of forces it not to overfit to one of the two problems it's trained on, maybe. I didn't understand that sentence that much, where they say, like, the boost in performance when combining losses might be because training with multiple losses reduces overfitting to queues, using which the model can minimize a particular loss. But I guess my understanding is maybe there's like, my understanding of it was that there may be some structure within the problem which allows the model to memorize the training set for with respect to the objective. So there might be like within a video, it can memorize the cue which says like this is related to this, which is related to this, but then that doesn't generalize to new settings. Something along those lines. That's just a spew of words about, because I was also wondering this same thing.
Mm-hmm. Okay. Next page. Yeah, I think it's the last bit of this. Well, I feel like actually it's, to me, it's sort of a similar thing, because okay, they mentioned because they don't need many labels, so it's a few short learning, and they But they only, let me see, they only need these 50 videos to be labeled. Yeah, but I guess the main takeaway here is like the same as that this combination of TCC and TCN, like it works best on this sparsely labeled data set. And for the phase progressions and the candle style, they figured out that TCC, like, wait, they performs better, but I forgot about this one. Okay, so for when training from scratch, yeah, I just focus this one. When training from scratch, TCC performs better on both dataset pouring and the pen action for both phase progression and candle style. But if you don't need to train from scratch, we have this pre-train a model, then the combination again of this TC and TCN performs better. So it's basically the same. Yeah, I think that's all. We have discussed a bit about the applications. So yeah, I think that's all about this paper. Any other comment? Anything I'm missing?
Yeah, I did have a comment about the applications. Thanks so much for going through the paper. Yeah, I was thinking, so the paper talks about sports and robotics, and then I was thinking maybe in terms of labeling some of the actions or processes in YouTube videos, or even in, for example, construction, maybe seeing the best practice on site. Yeah, so I was just trying to understand your thoughts or anyone's thoughts on where some of this cycle consistency learning can be applied, some of the domains.
Yeah, I think it's easily applicable in other domains. Personally, I think as long as there is this consistency on how an action is done. Like let's say if we pour something, that definitely we need to grab the glass and like lift the glass and do the pouring. So as long as the sequence of the activities are consistent, I would say this is easily transferable. I would say the issue is that when there is no standardized way to do something, and hence this sequence will not be generalized over different activities.
Yeah, or say for example, someone makes a mistake and they, instead of pouring, they go back. Instead of doing A, then B, they repeat A again. You know,
Yeah.
are there ways to overcome that? Or is it just through a lot of data, training data, of it being done right, that you overcome that discrepancy?
Yeah, like I imagine because this training method, we can detect this anomaly detection, right? So maybe in the case that someone wants to pour something, they already lift the glass, but then they drop the glass and the glass breaks, for example. That will be an anomaly. But it means that for the model to be able to learn that sequence, then we need to have enough data set that are standardized in terms of the sequence, right? To know that someone shouldn't, in ideal case, like someone shouldn't drop the glass and breaks it. So I think that's the point as well if we want to translate this in construction industry, like in more general case, like what's the sequence of the activities in a project. And it might vary different, like in particular construction, I imagine it might vary, depends on the sectors, like building a ship is different to building railway, but as long as building railway has general sequence, then it will be applicable.
The technique itself can be applied to any case where you have like a pairwise correspondence between two time series. And I think maybe one way it could be applied is to like what the physical science in terms of like natural disaster events or other kind of weather events, because you have in those cases like sensors in very different parts of the world, or even different types of sensors measuring physical data, and then maybe you could use it there. But I also think maybe in that case you do have a large amount of data, I'm not sure, to use, and this paper is more focused on the few shot case where you don't have a lot of data for a task, so it's hard to tell.
No, thank you both.
Cool. Are there any other questions? If not, we can finish a bit early.
Yeah, I do have a question. Jack here. Thank you very much, Inneke. That was very informative. I wanted to know, does it also applies if you have multiple actions within the video? So let's say like the paper focuses on a player throwing a ball, and if you have another video of another throwing a ball, it's going to try to align those. But let's say you have like 3 throws in one video, and another 3 throws, would it also be able to align like the first throw from one video to the first throw of the other video, so on and so forth?
Yeah, that's an interesting one. I think it relates to how we evaluate this as well. Like they mentioned here one.
Or does it assume just like one action? Because it might be confused. It might match the first throw from one video to the second throw of the other video.
My understanding,
Go ahead.
yeah, my understanding is that it needs to assume that it only has one action, because we don't. If we see how the loss is constructed, it's like we want to see the nearest neighbor, which in this case where we have multiple actions is that these 3 actions can be like all of they can be encoded similarly, and they can make these 3 nearest neighbors instead of one. And how they do the evaluation, like using this kind of style, they also mentioned that they assume there is no repetition. In this case, I guess that if we have multiple actions, like 3 shots, like three times of like baseball shot, then it means there will be repetition. And in this case, that it can get confusing, like which particular shot it refers to. That's my understanding.
Yeah, thanks. Thank you, Inneke.
Okay, I guess no more comments. Peter, what you want to add something?
No, so Isaac just asked a question, which was, how was the paper chosen? Curious to see if there's a repository of top paper. There isn't. I chose this paper, or I suggested it to Inneke because I thought it was cool. Because it combines cycle consistency with temporal data, and yeah, I thought it was interesting.
Yeah, and how did you come across it, Peter?
So before I worked at NPlan, I worked as a researcher in academia focusing on robotics. So I saw a lot of robotics papers.
Got it. Thanks. Thank you.
Yeah. Cool. Thanks everyone for coming, and have a good weekend. And hopefully we'll see you. I think we're going to do the next paper club in 2 weeks. So hopefully we'll see you in 2 weeks.
See you.